excited to talk about a concept that influences almost every decision we make. It's probability. In this presentation, I am going to show you an overview of how you can relate probability in real life. Before showing my presentation, I would like to request everyone to give your full participation. Ask any question when you have in mind. In the mid of the presentation also, you're free to ask. And now I can't see the comment section, so you can just raise your hand and any of my core members will assist me with the question. Okay, thank you. So let's begin. What is probability? At its core, probability is the measure of how likely something is going to happen, right? It helps us to understand the chances of a certain event occurring. Think of it as a science of uncertainty. In life, there are so many things that we can't be certain about, whether it's winning a game, going to in university, or attending your favorite band concert. This probability gives us the way to measure how likely things are gonna happen. It is not about predicting the future with absolute certainty. Instead, it gives about giving us an estimate of the chances, and that can be powerful. For example, what are the chances that India will continue to uphold a remarkable record in the upcoming chess Olympiad? We, anyone of you have watched chess live this Olympiad? Any one of the participants? Hello, am I audible, Shomo?
Mm-hmm. You're audible. Maybe no one
The
is
participants
following
must
chess.
interact, please.
Maybe no one is following chess Olympiad nowadays. Okay, go on.
Okay, fine. But please interact everybody. Then only we can. First, I would like to know that how many foundation members are there. I mean, my students that who are pursuing foundation, please raise their hands. How many are there? I can see the screen. Wait. Only. Okay.
Okay, let me see. Two, three
Okay.
people are raising their hand.
And the rest are from diplomas. Okay, fine. Please don't comment now. I can't see the comment section for a while. Try to
Yeah,
interact, any
don't
one of
read
you.
people.
Okay, okay, thank you. So, coming into the next example, that is what are the chances coming into. Hello, sorry. What is the probability that you will get admission to your dream university? This is also unknown, right? And let's not forget about your personal dreams, that what is the chance that you will be lucky enough to attend your favorite band's concert. Sure, it depends on things or factors like availability of the tickets, the timing, or the prices, whether you can afford or not, and the time that on the time span that there will be, means the certain dates on where the concert will be held, right? So all this situation probability is about understanding the uncertainty and randomness. Every examples that I mentioned, there is something kind of uncertainty, right? We can't say whether yes or no. So coming into the next slide, about that we will elaborate more about uncertainty and randomness. Here is a random experiment, a key to analyze uncertainty. Now, what is random experiment? Does anyone knows? Can elaborate, please? Anyone? Anyone? I think I need to elaborate to you all. Okay. What is a random experiment? Random experiment is a process that leads to certain outcomes, right? It is one of the key tools in probability that allows us to model real world situations where outcomes cannot be predicted with certainty. Random experiments are used across various fields, like especially I have highlighted the three fields, major fields. Firstly, the medicine and clinical trials. Here, RTH system has been conducted daily to test the effectiveness of new drugs in the medicine department. And the fourth department, if anyone has pursued economics in any other degree or any other side by side degree, if you are pursuing economics there, you have heard of the term game theory, where they plan strategies about and they analyze the game, and then they make their move, right? So here also random experiments are used by sports analysts to stimulate possible outcomes, how to win the game, or what which player should bowl now in this over so that we can get the maximum wickets, that this kind of strategy they maintain. Similarly, in case of the big insurance market or loan market, whether it is risky to provide an is to risky the whether it is risky for the individual to take the loan, or whether it is risky for the insurance provider to provide the insurance, just for say example car insurance, health insurance to the insurance taker. Probability plays a key role in this context. Another markets where random experiments. Now I would like, okay, fine. So my question to you all, like, why we are doing probability, why we are doing random experiments? We have certain in target, like you won't pursue a degree without having certain targets in mind. We are not doing this degree without having certain target, right? We have the target that yeah, we will learn python in this part, yeah, we will learn we will get to know more about machine learning, deep learning, statistics, whatever. We have certain objectives, we have certain targets, right? Here also we have certain targets, that's why we are performing this kinds of random experiments. There lies the concept of probability event, making decisions under uncertainty. Consider the same examples that I have used earlier in my slide. What is probability event? Probability event is simply the outcome we are interested in. And we use probability event to estimate how likely the event is going to happen. Just for say, for the medical department, we can use the event is if the probability of success with the new drug is significantly higher. If so, if so, then our drug is effective. Before testing, before giving covaxing to everyone, the scientists have tested on means every animals, on humans, everybody. If the body suited, the probability was high, and thus the drug was effective, and everyone got covaxin, right? Similarly, for the sports, the planned strategies predict outcome, like what is the chances of winning the championship. They make specific game decisions. And similarly, for the loan market or whatever, like when a person goes to a bank, just for example, uh, what are the factors? Means they ask, just for example, a person is going to the bank, and now he's asking for a home loan. Okay, uh, does the bank give immediately? Does the bank immediately give the loan? No. The bank asks for certain requirements. Requirements are the person's salary. Will the person able to repay the loan? Otherwise, it will be risky for the loan provider, right? Similarly, for if a person goes and asks for a car insurance, the insurance provider will see that what is the chance that the person will not hit the car randomly, means often. Uh, They will have a research on that topic, like it will insurance providers, they will have a research on certain factors like the location, whether it is situated in the hilly region or the normal region, for what type of car it is being used, and everything. If it a sports car, then the insurance provider will charge high premiums, and if it's a normal car, then the premium percent is comparatively low. So for all these cases, probability is more than a mathematical concept, right? It is a tool for making informed decisions. Coming into the next slide, types of probability. Classical probability. We have heard of this. We know. We majority of us know about it. What is classical probability? Classical probability works when the outcome is known. What total probability? Then total outcome, total possible outcomes is known in advance. Just for example, tossing a coin or throwing a dice. For tossing a coin, we know the probability of probability is half, as the coin has only two faces. And for throwing a die, we know the outcome is total possible outcomes are 36, right? So everything is known in advance. But if what if the case in real world, not all the possible outcomes are known in advance, right? So in that case, probability, classical probability doesn't work well, effective. thus many stat- statisticians Thus that's why many statisticians built up a more better approach to measure probability, keeping in mind the real life scenario. Here lies the concept of experimental probability. The experiment, whether in experimental probability, we work on observed data, the events that had occurred in the history, occurred in the past for the successive dates. But if, just for example, here I have taken whether it will be raining tomorrow or not, we can just look into the weather conditions of the past 100 days or whatever, then we predict, and then we actually get the probability. But this, when what happened when enough data is not available to you, just for example 100 days data is not available, only 2 days data is available, or any of the data is not in the meet is not available, right? Then this kind of experimental approach of probability doesn't work. So in these scenarios, another widely used approach in the support of the real life scenario, when there is no support, sufficient data, has been put forward by the statisticians. It is the subjective probability. It is the most effective probability. Here, in subjective probability, is based totally on personal judgment or personal emotions or whatever. Like when a particular brand, just for example, chips Lace is trying to introduce a new variety of chips in the commercial market. Now how they will know that this variety will give them their profit? They will held a survey. Or each of majority, they will take a sample, and of that they will have a survey, and they will ask each and everybody their personal preference, how they test it, they like it or not, how would they rate it. In that personal judgment, they will form a graph, they will form probabilities, measure probability and all, and on that basis they will launch that product. So but subjective probability is totally upon personal judgment, right? And it we know that personal judgment varies from people to people. My judgment, like I like this new commodity of, and I like this new brand, what Lace has dropped, but you may not like the same chips, right? So personal judgment or personal opinion varies from people to people. In that case, subjective probability for a large data sample or for a large data is, it's kind of complication, leads to more complicated issues. Thus, A new approach has been launched, that is axiometric probability. Here, the data set is wide. Axioms wide. It's a big large letter. Here, what is axiometric probability? Axiometric probability approach follows strictly mathematical rules. The probability of event must sum up to one, and it's based on axioms. Axioms means rule that apply to any probabilistic models we ensure. Coming up to my last slide, where I will be reading, where I will be listing some job names. These are the most highly hello. Okay, so here is the application for probability in real life. There are some job roles that is been highly been active in this
Okay, I
real
guess
world.
we have a question.
Yeah.
So, yeah, Raghuvalam. Yeah, you can ask the question, Raghuvalam. Are you there? I guess he's not here. Okay,
Okay, I'm
it's
continuing my part. Later on, I will ask him again. Okay.
okay.
So you see that here is some. I have listed some four major job roles. First is the meteorologist or the climate data scientist. How they use probability, you may ask. Like how this job role uses probability. Probability is used here to predict the likelihood of weather events like rainstorms or temperature changes. Meteorologists collect historical data and use probabilistic model to forecast weather. Like there's 70% chance of you have heard in the news right every day. There's 70% where the news reporter tell that there's 70% chance of raining in this region, but 70% chance is not probability ranges. We know that value of the probability ranges from 0 to 1, but it is not necessarily accurate. Okay, there's 70% chance. Similarly, in the machine learning and AI field also, probability plays a major role. Some if you are from the data science level, sorry, diploma level, then you must be knowing that how probability plays a major role in machine learning, while encountering with the diploma in data science. Here, probability helps algorithms making decisions, predictions, or classifications based on data. Okay, for example, a recommendation system like Netflix, Spotify, or YouTube. We use this software every time. Majority of our use it. They use what they do that they use probability to predict which movie or song you're likely to enjoy, right, based on your past preferences. Like you search kind, like for me I like Harry Potter kind of series, and or thrill or suspense or detective kind of series. Then the Netflix which understand or YouTube which understand that he she likes this kind of this genre, so they will recommend more on this topic, right? Here comes the applications of probability. Similarly, the third here we have you have seen there is an Amazon logo. Supply chain operations or logistic analytics, what they do, they use probability to predict demand, optimize inventory level. Inventory is nothing but the stocks, and manage uncertainty in the supply chain. For example, e-commerce companies like Amazon, Flipkart use probability to forecast how much a particular product they will need in different regions to overstock or running out of the stock. They have their market in everywhere across India, right? So they know, like for example, keeping as much as sweaters in the Darjeeling or the hills region, just for example, will be profitable for them, and keeping normal summer dresses and everywhere in the one second. Okay. So, in the normal regions like Mumbai or Kolkata, cotton clothes, cotton kind of clothes, it will be profitable for them because there is a certain factor known as delivery time and all, right? So, and the last thing is the sports analyst or the data scientist. What sports analysts use probabilities to simulate various game scenarios like and outcome, access players' performance, like this player is going good, this player is going bad. They also have a clear view on the pitch, on the cricket pitch, on the ground floor, or the where the game is going to happen, everything. Uh, what they do that before any football match or cricket match, the analysis or the trainer have a clear view of which players gonna play well in this over, or which bowler gonna hit maximum wickets in this over. This all the tasks they plan it before. If the just for example, if they have not planned before, just the chess olympiad I say, uh, every members you see, whether it's Prag, Bookish, or the women's chess members, they plan everything. They plan the strategies. Otherwise, Prague would not wait. Any of the, I mean, Prague not only. Everyone will not be so much outstanding on their performances, right? That's all. So probability is necessary in our real life, especially for jobs. We are all doing this degree to have a good job in future, right? That's all from my side. Now I would like to request my friend Shukanya to carry on with the next. Any questions? Any questions?
If you have any question, you can ask regarding the part we just covered. Okay, I guess no question.
No
Uh,
question. All good.
okay. Uh, Nice presentation, by the way,
Thank you.
Shamila. Yeah, I would like to call Shukanya if to start for the next part of the uh, probability sections. Sukanya, are you there?
Yes, yes. Thank you. I was
Yeah.
just waiting. Yeah. Thank you. Thank you, Shravana and Sankata. Okay. Uh, we'll continue along the same lines like what we were doing now, and we'll see how how to go about from a random experiment. As of now, what we have done is we have conducted a random experiment. We know what is probability, and we have an idea, right? We got an outcome, and we have steps with us. Now, what to do with this, or how to calculate the probability? How does it change in different scenarios? Or you saw there are so many applications for probability. Similarly, maybe after this whole presentation, you can go and try. There are so many since you have all crossed the foundation level or somewhere around it in CT and all, you might have seen, right? Like problems like Monte Hall problems and other stuffs. And probability is a very basic of statistics. So there are so many paradoxes out there which are much more interesting. And as you along the way you will see, statistics is one subject, especially probability and other distribution theory is one subject that you can very closely relate to with your day-to-day activities. There is no need to think of very complicated systems or issues with it. You see random experiments around you all throughout. You do so many random experiments through your way, actually. So let us see how is our mind actually calculating the probability unknown to us, or how are we moving about it. So then we'll first go through the probably the main points out of it, or the main definitions. So first comes what is a sample space and events. Now you conducted a random experiment, as just Shabna told. Some you when you conduct a random experiment, let us you conduct a trial, you conduct an experiment repeatedly, or you conduct it even once. You have a set of outcomes, all the possible outcomes. The when any for any experiment we have a possible set of outcomes. What makes it random is that we don't know what outcome we will get as a result of that particular trial, right? That is the only thing that is making it random. As a whole, the random experiment thing, you always have set of possible outcomes. Now all the collection of all these possible set of outcomes, That is what is called sample space. Okay, sample space. What are the possible set of outcomes for a random experiment? And if you take any one of the outcome out of it or a combination of outcome out of it, they are said to be events. Okay, so sample space is just the combination of all the, or the set of all possible outcomes. And when you pick one outcome out of it or a set of combination of outcomes out of it, it could be defined as a symbol. Now, this is one example maybe that all of you could relate with. You're all BS degree students. Now, out of this BS degree students, if you could actually find out who are the students who are passing out diploma this year, okay? Or if you want to go along a very simple line, probability is never explained without a card game, coin toss, and a dice experiment maybe. So, if you go with a very basic thing, if you toss a coin, what do you think is a possible outcome? If you toss it just once, your possible outcomes are either you get a head or a tail, right? There is no other possible outcome in it. If you toss a coin, you get either of these outcomes. So that consists of your sample space. Now, if I simply say what are the possible what is the favorable outcome to getting ahead, so you just have one outcome favorable to it, right? But in case of maybe a dice experiment, when you throw a die you have six outcomes, either of the phases, 1 2 3 4 5 6 could come. Now if I ask, if I take an event, what is the an odd number is obtained, you have your favorable cases as 1 3 5, right? So there are more, not just one outcome, there are a set of combination of outcomes. Now whatever I define as one head or a um, odd number as an outcome, these are defined as events. So this is one example, I guess, that you could all relate. If you find out, if you want to find out, you're conducting an experiment of who would pass complete their diploma in 2024 of your degree. So you could say that all the students doing the diploma level of the course is the sample space, right? That consists of all the students, and any number of persons could actually pass. Now, if I could define just how many boys are there who would pass, that's a probability case. You can't really exactly tell what is it, but you can always say it ranges between 0 and 100. You know the possibilities, you just don't know what is the exact figure. Okay, and you could find such infinite number of events out of it, but I'm moving forward. And if you could just recall quickly what Shavna said, the final one, which is actually, sorry, what, watch the movie Moneyball. It's a movie that drive into the film. Okay. Yeah. Okay. So finally, if you could, the final important definition of probability, that is very widely used and that actually overcomes almost all of the drawbacks or shortcomings of your other definitions of probability, is actually axioms of probability. If you can look into the limitations of others, like if it's an infinite sample space, few definitions are not applicable. One definition is very biased. So overcoming all that, you have a general definition which is widely used by us statisticians, all of us, and that is axiomatic probability. What are the axioms of it? What are the rules that we are supposed to have when we consider the axiomatic definition of probability? First rule says that for any event, that is any outcome or any combination of outcome that you take from the sample space, the probability related to it is going to be a real value and greater than or equal to 0. Now, if you go by the standard definition that you all know, what is the definition of probability? It is always a ratio to number of favorable cases to the total number of trials, right? Now, either there is a minimum possibility where none of the outcomes given in the sample space is favorable to you. That means the numerator would go by 0 and the total number of trials would be the probability ratio. Now that would mean that the probability is 0. Okay. Or what is the right extreme that you could get? That you could get is everything out of your sample space is favorable to you, right? Any of it could occur, all of them are favorable to you. Now, if all of them are favorable, what would be the definition of probability? It would go by number of trials divided by total number of trials, right? Because both of them are same value. Now, what would that probability be? It would be 1, right? That is why the probability of sample space is 1. That is, any one of the outcome is for sure will occur, right? Any one of the outcome is automatically, it's just given that one of it will come out. So the probability of a sample space is 1, and the probability of any event is going to be a real valued function which is greater than or equal to 0, because that is the minimum value. And the final axiom of probability states that for a disjoint set of events. Now, what is a disjoint event? Disjoint event is when two events does not have any common point out of it. Okay. Now, if I'm just uh, stating an example of maybe we are actually mapping all the students of BS degree who are doing the diploma level, going on with the same example. If it is just from the diploma in data science and diploma in programming from different states, you could actually have common points, right? If you actually take it state wise, you could see there are persons doing either of the diploma, both the diplomas, actually mixed way or something or the other way from every state. So you have a common point. But on the other hand, if it was a dice experiment and you're stating your two events as one is a you're getting an outcome of odd numbers and the other is the set of outcome of even numbers. What would be the odd number count? The most favorable outcomes, it is going to be 1, 3, 5, right? And for the even numbers, it is going to be 2, 4, 6. So there are no common points between these two sets, right? These two events have no common point in them. Such events are called disjoint events. So what the axiomatic probability states is that if you have a set of disjoint events, the probability that either one of it will occur. What is the probability of either one of them, or what's the definition of either one of them? If you could actually recall from the matriculation of your set theory, what you have studied in the matriculation age of yours, say either of the events, either of the set happening, that would actually be the union of the sets, right? Union of these sets would be stated as the either of the events. Now, either of the events happening would actually be equal to probability of either of these events happening, which actually be equal to sum of their individual probabilities. That is what the final axiom of probability states. So if you have disjoint events with you, you could just simply add up all the probabilities, all the set of disjoint events probabilities to get the probability of either one of the set to be your outcome. This is what axiomatic probability states. Do you have any issues till now or any additions, inputs, anything till now? No, if you don't want to speak, maybe you can put an emoji or something. No, you'll not interact. Okay. But if you don't interact, we have no idea that if you understood or not. Okay. Try to give some response of some kind if you don't want to talk at least. Or if you really want to add something, also go ahead. Yeah, yes, Sharad. Shararat, sorry. You can speak up if you want to.
Yeah, you can unmute yourself and ask the question.
No issue, ma'am.
Okay, okay, great, thank you. Okay, so let's move on again. What is the next part? It is the conditional probability. What does conditional probability says? Now, conditional
Please
probability
mute
we
yourself,
calculate.
Shararat Al. I'm sorry. Yeah.
Thank you, Sharana.
Hello.
So what I said, thank you. Hello,
Yes.
Please mute yourself.
am I audible?
Thank you. Yeah, you can go.
Hello. Yes. I have no.
Hello.
Is disjoint events and independent events are the same? No, not necessarily. Disjoint events are not necessarily always independent. They are different. I'll discuss the concept of independence just in a minute. Okay. Disjoint events just mean that you don't have a common point. Okay. Between two events, you don't have an intersection. You have no common points in them. Independent event would actually mean that there is occurrence of one event or one outcome is not affecting the occurrence of another one. Okay, this is the basic definition difference. I'll elaborate in a minute. Okay, so what is conditional probability? We calculate conditional probability only when we have some prior information regarding some outcomes or something about our random experiment. Maybe you had it before the random experiment or you had it while doing the experiment. Some way or the other, you already have some knowledge. For example, think that you are flipping a coin two times. Okay, you are flipping a coin two times and you already know what is the sample space when you flip a coin two times. You could either get two heads or you could get both the tails, or you could get one head and one tail, right? Which could be written in two different ways, that is head tail and tail head. But still you have four different sample points, where one is both, it is both of them are going to be head, the other one is both of them are going to be tails, and the other one is one head and one tail on two different combinations. Now consider that you already know there, you're sure that both of the trials did not result in a tail. Okay, you're very sure about it. You already have that information from somewhere, through something you already have that information. Now that is a prior information to you. When that happens, what do you think will happen to the sample space? The sample space is being truncated, right? It is going to be shrinked out. And what would be the resultant sample space? It is going to be both the heads, or one tail and one head, right? These are the only possible combinations in it. Now the probability for the outcome of two heads in the first case, when you had all the four possibilities, was 1 by 4. One was just the favorable outcome, HH was your only favorable outcome out of the all four outcomes. But when it comes to the second case, where you know that both of them were not tails, your sample space is being restricted and you only have your sample space as HH, TH, and HT. You only have three elements in it. Now the probability for the same event, that is two head, is going to be 1 by 3, right? Now the probability has increased from 0.25 to 0.33. The probability has got some change. That is what conditional probability conveys to us. So conditional probability is telling us what are the conditional probability used when you have a prior knowledge, and what it is telling us on the knowledge, or when you have a prior knowledge as something has occurred, what is the probability of another event. Okay, clear? Like if you go to the first example that we do, if you are looking for 2024 pass out students and you want to know how many girls are there in it, already your sample space is shrink, right? You don't want the whole population, you just want to know how many girls are there, and then you want to know how many of them passed out of it, right? That will give you the proportion or the probability that we are seeking for. So that is what conditional probability is telling us. Now if you look into it purely in mathematical sense, you can give the definition as probability of A given B, where A and B are two events, and B is the information, B is the event with which you already have an information. Then probability of A, that is when you already have a prior knowledge regarding B, when the probability of A given B is going to be equal to the joint probability of A and B occurring. Okay, the joint probability of A and B occurring to the ratio of that to the individual probability of B occurring. Okay, that is going to be the mathematical definition of it. From this definition, you can also understand or derive that the joint probability for A and B occurring together is actually going to be probability of A given B into probability of B. I'll tell you in a minute why we need that. But yeah, you can deduce it from this information. Now about what you were asking about independence. Okay. This conditional probability is affected only when the events are not independent or dependent. Why is that so? Because what the conditional probability tell you? Conditional probability tell you that event B has already occurred. Now what is the probability that event A will occur? Right. Now if you think that A and B are independent, what does independent mean? Independent just by definition means that occurrence of one event is completely unaffected by the occurrence of another event. Such events are called independent events. Let us take an example out of it. You flipped a coin once, okay? You got some result out of it. You got a head or you got a tail. You got some result out of it. Do you think the second time you flip a coin, it is affected by what you got in the first time? You are doing it independently, right? You're complete, you have tossed a coin, you got a result, that's it, done. Now you're completely doing another round and you're just flipping the coin. Now you with your common sense, I guess, you actually know that it is unaffected. It is completely unaffected in the second time. Such events are called independent events, right? Now for say you have CET and Math 1, you passing CT in this term is not affected by whether you pass Math 1 or not, right? It is just dependent on whether you study or not. Okay, so passing Math 1 and passing CT are going to be independent events. But at the same time, if you know that you have not at least watched the last 2 weeks of your CT and you are just going to attempt your examination, maybe your share percentage that the event is that you get a score of 95 or above might slightly be lesser, right? The probability that you would get such a high score if you have not even watched the lecture is going to be slightly lesser. Such events where occurrence of one is affecting the other, okay, such events are called dependent events. Now, why is for independent events conditional probability irrelevant? I've given here more examples if you want to look into it. Like you already know, like while during COVID, sales of luxury items like gold or bike or something like that, you wouldn't spend money on such a crucial time on luxury goods, right? Unless we are some rich, very super duper rich people, we don't usually spend such on luxury items. That is the sales because of COVID has occurred. The sales of such items had gone down. But at the same time, if you look for the sales of groceries or provisions that you use, we cannot live without that. That is our basic need. On such items, the COVID has not given much affection. Much it has not affected much, right? So you can differentiate what are dependent and independent events like that. Now, why does conditional probabilities? Why is it is completely unaffected by independent events? That is because the joint probability for two events A and B, if they are independent, is going to be equal to probability of A into probability of B. It is like you want both of it to occur, but the other is not affected by the other one, right? Like one is not affected by the other one. So this probability will become mathematically, it is going to become probability of A into probability of B divided by probability of B. Now probability of B would cancel out and you would get probability of A given B is equal to probability of A. That is, happening or non-happening of the event B does not affect the event A at all. Okay, that is why conditional probability is relevant. Even if you have a prior information, it is relevant to calculate it only in case of independent events. Okay, good till now? Fine? Any issues? Okay, great. Thank you. Now, something addition to it. Law of total probability. Suppose we want to calculate. Okay, thank you, Shubha. Yeah, suppose if I hope you remember, I'll just refresh your memory probably. The rectangle. This is a Venn diagram. If you know, we usually use a Venn diagram for the diagrammatic representation of our sets. Say this is your sample space, okay, which is the universal set if you state it in terms of set theory, and this is the universal space, and you have events given, you have events or set of outcomes inside the sample space. Okay, now such items are usually represented in ovals or circles in general set theory. Now suppose that we want to calculate the probability of this particular event A, which is represented as an oval here, and you have a set of outcomes already. Okay, you have a set of partitions already. What are these partitions? A b1 b2 etc bk, which are simply disjoint events. Okay, you have disjoint events. Do you recall what is disjoint event? That there is no common point between b1 and b2. They are disjoint events, right? So you have such the collection of all the disjoint events that constitute your sample space is actually called the partition. And if you have the partition of A of your sample space and you want to calculate the probability of the occurrence of A, what is the probability? The probability is simply this portion, the left end of the portion, which is actually what? Probably A, the set A portion intersection with B1, right? The joint probability is actually going to be A intersection B1. The second portion, like that is the larger portion over here. This happens when B2 intersects with A, right? That is where this section happens, and so on. And to the right, and you can see that where the BK intersects with A. That these are the different partitions that you get, or event A occur with respect to the partitions on these intersections. That is A intersection B1, A intersection B2, and A intersection BK. Now, what will be the total probability, or what is the chance that the event A will occur? What event A would occur? if A is intersecting with, or you get a point from anywhere of these partitions, right? You get a point in the intersection points of anywhere of this partition. That is, you get a point from A intersection B1, or you get a point from A intersection B2, or you are getting a point from A intersection BK. Now, what would that say? That say that the total probability of A occurring is actually going to be probability of A intersection B1 plus probability of A intersection B2 plus etc. probability of A intersection BK. So if any of these intersection happen, that is why we are adding up the probabilities. Event A would occur if any of these intersections happen. So probability of A intersection B, the total probability that A is occurring is going to be probability of A intersection B1 plus probability of A intersection B2, etc. probability of A intersection BK. Now, from what we had actually gleaned from summarized from our conditional probability was that probability of A intersection B is actually equal to probability of A intersection B, sorry, A given B is equal to probability of A intersection B divided by probability of B, right? What we deduced from there, the intersection is going to be equal to the conditional into the individual or the marginal one. So that is probability of A intersection B into probability of B. Now using this formula, if I am substituting into each of these intersection, what would I get? Probability of A given B1. That is probability that A will occur when we already have the information that B1 has occurred into the actual chance that B1 is happening. Okay, the actual chance that you are getting a point from here, you actually got a sample point from the event B1 and it is intersecting with A. We need both the probabilities happening together. Only then that will happen in the intersection, right? We want a point from B1 as well. It should be from the intersection. If you are getting a random point from this area, that is actually not going to contribute in any way. You should actually get it from the intersection. That is what these are saying. Probability of A given B1 into probability of B1 plus probability of A intersection B2. Similarly can be written as probability of A given B2 into probability of B2, etc. Probability of A intersection BK. The last section could be written as probability of A given BK into probability of BK. This is what the total probability, law of total probability says. This is the mathematical representation of total probability. So total law of total probability is simply it is simply stating what is the probability of occurrence of one event A with respect to the set of partitions of the sample space that we already have with us. Okay, now using this, we are actually going into something very widely used known as Bayes' theorem. I guess if you are already in the diploma level or like if you have already completed the foundation level of stats 2, you might have come across Bayes' estimation. It all comes from the same scientist. This is the basic also out of it. If any one of you can recall, it actually says the posterior probability is actually proportional to the likelihood into prior information. Now let us just understand what are these terms. Prior information, as you saw before, is actually the information that you already have with you. Okay, information that you already have with you, that is actually called the prior information. Now what is likelihood? Likelihood is nothing, just the joint probability. Okay, the joint probability of all the events or all the things that you want to have, but on the light of what? On the light that you have already a prior information with you, or purely stating, it is actually going to be what is the chance that we will get a sample, okay, a sample of a particular format if we have a knowledge about some event already happening, or if we have some already information about our parameters or about our events. Okay, so likelihood is just what is the probability that we will observe something based on some already given prior information. So when you combine that likelihood together with the trial, you get an improved probability in terms of what? In terms of accuracy. Okay, you are improving your result. When you already have an information, you are trying to include that into your probability and include and improve your accuracy level of your result. Okay, now if you could think like what you already have an information that there has been floods in the north. Now that information can actually give a chance that there would be a spike in the wheat, right? Like wheat comes most from there probably. So there is a chance of occurrence of such thing happening. Okay, or you know that what the there's going to be some, due to the Russian war, there are going to be petrol drop in the petrol prices. So probability there is a very, maybe very 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 small chance, but still there is a chance that the sales on bikes would go increase, or the petroleum vehicles could go increase, or something like that. If you could just deduce some example that you could understand from yourself, or you could say that the exam difficulty level was very hard. Okay, it was very very hard. Half of the students were not able to solve even what 50% of the questions, then you know that the chance for more than 90% of result from your exam is going to be a lesser one, right? So you are trying to incorporate what you already have, the prior information, to the observed sample, and trying to gain a better probability out of your event, for a particular event. So that is what is stated here. For a particular event, when you already have some evidence, the posterior probability, that is what the Bayes theorem says, the posterior probability is actually equal to the product of the conditionals into, that is the likelihood, into your prior, divided by what is probability of E. Probability of E is just simply the total probability that we saw here, the law of total probability that we just observed here. Okay, maybe you can try up different scenarios. Okay, you're just drawing a card from your deck, and you already know that in the deck you don't have any more kings left. The king is with somebody or the other. You already know this information. Now what is the probability that you would get a face card, right? You could actually calculate such numerous probabilities. There are so many types of events that you can define by yourself, for simpler things that you can see by yourself, and calculate the different probabilities and see how improved the probability is based on the data that we have. That is why the study of statistics or study of data is more relevant now, because from the data you actually can derive so many useful information if you know how to derive it, or if you know what are the theories that are running behind it. Okay, so to just summarize what I discussed now, first was sample space and events. Sample space was just the sum set of all possible outcomes. Event was one or a combination of outcomes that you have from your sample space. Any of such things that can be called as events. Axiomatic probability states that the axioms of probability are, for any event A, the probability is going to be a real valued function, or a real value which is greater than or equal to 0, and the sample space probability is going to be 1. Okay, that is any of the outcome would actually come from the sample space. So the total sample space outcome is actually going to be 1. And for the disjoint events, the occurrence of a set of either of the disjoint events is actually simply equal to the sum of all their individual probabilities. Now conditional probability and independence, you have independent events are one which do not is not influenced or affected by one another, and conditional probability states that when you have a prior information, the joint probability divided by their the prior information that you have will give you a condition probability. That is, when you know that event B has occurred, the conditional probability gives you the probability of the occurrence of A. And total probability states that when you have a set of partitions of your sample space, a disjoint set of partitions of your sample space, the, the probability of A can be calculated as the sum of their intersections. And Bayes' theorem summarizes you what is the possibility of the occurrence of an event when you have a prior information. You can get an improved probability by incorporating it with their corresponding likelihood. Okay, that is it from my part. Thank you so much, and please do go check out the different paradoxes you have. Any doubts before I hand it over to the next person?
Okay, great presentations, Kenya. So,
Okay.
guys, if you have any question, you can ask.
Okay, on the way to also you can, if you have any questions, just ping in the chat box. Okay, without, I'll just hand it over to Samyavrata for the final version. Thank you so
Okay,
much.
so thank you. Okay, let us start for the next part. um, so much visited and popular part of probability, that is random variable. Okay, let me just set up. And yeah, here we go. So basically, what is what do you mean by the word random variable? Anyone? Anyone? I would like to get responses from your side. And even if you feel bored, you can react. There's angry react as well. If you don't like the discussion, then also you can react from over there. Okay. Anyone interested to give answer of what is variable or what is random variable, to be very specific? Okay. So let me discuss only then. Random variable. Initially, the idea pops into our mind by the word random variable, that it must be a variable which is random, right? But in reality, it's not the case. So random variable is actually not a variable, it's a function. It's a real valued function which assigns real number to each sample points. Now what is real valued function? That means the codomain of the function is the real number set. I'm pretty much sure that you all are aware of the term domain, codomain, range, right?
Yes,
So,
yes.
yeah. So, uh, this is a function which assigns real number to all the sample point defined over the sample space. Okay, pretty straightforward, but but it's little boring, right? How someone came up with this idea of random variable, how someone came up with the idea of assigning real numbers to those outcomes, right? So it's a question, so we should be solving that. Try to ponder in that way. Okay, so basically, um, let us define something first. Let us do a little bit of maths. Okay, suppose we have a sample space corresponding to a random experiment E. Okay, the sample space is omega. Now let us take a power set of this uh, sample space omega. Okay, so we call it sigma field. We call it sigma field um, in terms of measures or measure theory. Okay, so this is a sigma field. Let's name it script A, and the sigma field be the power set of the sample space only. Okay, similarly, we gonna define another sigma field which will be taking elements in this format. uh, this is a range of a subset of real number set. Okay, this is a subset of real number range where a is a real number. So this is also a sigma field. This one is called Bodel field. So this is called Bodel field. Now, why I am discussing these irrelevant things? So, let us make it relevant now. Let us define a probability space. There's something called probability space, and how does that look like? Uh, probability space. Probability space is a power set, is the sigma field. Okay, sigma field which has been generated by the sample space omega. That is script A. So we're gonna define probability space omega and sigma. So basically, omega and script A. Script A is the sigma field generated by the sample space omega. Now, let us define a similar probability space based on Bodel field. So that is generated from what? I just mentioned on the last slide. Can anyone tell me that Bodel field is generated from which set? Anyone? Hmm. Anyone? Bodel field is generated on which set? No one will bite. Don't worry. Okay. Okay. So this one is generated by real number set, right? It is taking a. Uh, it is taking what? It is taking a real number range as its element, right? So this gonna be another probability space, that is real Bodel. Okay. Now let us define a function x which gonna take this probability space as its input and map it to a different probability space that has been taken Bodel field in count. Okay. And x should be invertible. Okay. So what does that mean? Inverse of x, and which should take a range as input, uh, where a is a real number. This should give what? This should belong from this sigma field script A, right? That means omega, let omega be a element or omega be a outcome. Okay? Sorry. Okay. Omega be a element of our sample space, then this is the range where x will be lying, or this is the real number range where x will be lying, right? Till now, any doubt? Anyone? Yeah, Utkarsh, any doubt?
No, no doubts.
Okay, so let us accelerate a little bit. Okay, so a random variable is such a variable which is assigning a real number to all the sample points. It's true, simultaneously it should have, okay, it should have uh, it should have a inverse which belongs to the sigma field generated by the sample space only. Okay. Now let us define a function on this Bodel field or the output. Okay. Let us define a function px. Okay. Px on the output of the uh, random variable x. Okay. We will take output of the random variable, what was generated by the random variable. Basically, what was generated by the random variable? It was a probability space, right? So it should be uh, this x which belongs to this one, right? Now I can simplify that and write it like this. Okay, as x is depending on the x is the natural ideal number which on which the range is depending. Okay, now is this function directly connecting me with the sample space? No, it's not. It's defined on the Borel field. It's defined on the real number. It doesn't uh, connects me to the actual sigma field, which I actually generated from the sample space, original sample space omega, right? So what should we do? We should take the inverse and define another function called p, okay, which is defined on the old sample space and sigma field, but it should take this as the input. How we can pursue that? To pursue that, what we can do, we can pass this input through a inverse function of inverse random variable function, right? So if I pass this, then only it will get generated, right? And by x, what I am trying, by small x, what I am trying to mean? I am trying to mean a range, right? This range, okay? Now this function is actually giving me the probability. Okay, so this is a probability. So p should always lie between 0 to 1. Okay, this is a probability function. Okay, but don't confuse, px must not be a probability function. Okay, now this is actually giving me the probability that x inverse will belong to this range. I mean, what I mean is, uh, sorry, uh, x inverse will take input a range, take input this range. So basically, probability of x giving output of this range, basically that means if there's a graph and there's a point x, minus infinity to x will all be covered inside this probability function. So this is accumulation of the frequency of the probability. So this function is popularly known as df or cdf. Okay, understood? Any doubt, guys, so far? If you have any doubt, you can ask. Okay, so based on this uh, nomenclature, or based on this df or cdf, what we can do, we can classify random variables in three parts. Those are discrete, continuous, and mixed. But how come? How we can classify those random variables based on the CTF? So basically, uh, let us define in context of continuous random variable first, and then we will go forward with discrete one. Okay, so what continuous random variable says? A random variable having a CDF f is said to be continuous if f is everywhere continuous. Okay, so the function, suppose this is a df function. Okay, uh, x, and this is df of x. So I shouldn't be allowing any break or jump point or any discontinuity point on the graph in terms of taking a random continuous random variable. So if the graph of df is continuous everywhere, by everywhere I mean on the real number line. Okay, so if it is continuous everywhere, then only I can say that the variable, the random variable is a continuous random variable. Okay, now there are two types of uh, continuous random variable. First one is absolutely continuous, and second one is singular continuous. Any idea, guys, how they are different to each other? Like, what's the relevance of defining two different type of continuous random variable? Anyone? Okay, so basically you guys are already aware of that in case of continuous random variable we gonna be including something regarding integration, right? Okay, so basically if the function f of x can be represented as this one, as this format. Okay, so as this format where f of u, small f of u, is defined, is a valid function, and by the integration I mean only Lebesgue integration, then only I can say that f of x, the CDF, is a absolute continuous random variable. Okay, and we already know that uh, not all functions are integrable, right? If fx is such a function that can't be represented as an integration of a valid function, then we can't say it an absolute continuous random variable, no matter what the graph of capital Fx appears to be. Okay, so in that scenario we call it singular continuous random variable. Okay, now comes the very essential one, but we're gonna discuss it. We are discussing it a little later. So discrete random variable. So what is the meaning of the word discrete random variable? Again, I'm asking in spite of getting no response. Anyone? Okay, by the way, do you guys have any doubt for the previous section? So so far we were actually defining the the random variable and its CDF, and it was integrating and all, right? So in this scenario, integration doesn't work, right? Even if works, then also it will not be fruitful. So what should we do? How can we define? Uh, how can we check if a random variable is not continuous or of any type by looking at the different DF, distribution function? How can we say that? Basically, suppose we have jump points in the graph of DF. Suppose this is the graph. Okay, this is called step function, if you are aware of. So suppose we have a step function diagram uh, as a DF function, DF, distribution function. In this scenario, what we gonna do? We gonna create a set called E naught. It is a set of jump points on the all jump points on the graph of DF. Okay. Now, if the cardinality of E is either finite or countably infinite, then only I can say the random variable of which we have obtained the DF is a discrete random variable. Okay. Now, how to assign probability? If there's a random variable, there should be probabilities, right? So, we're gonna define the probabilities in such manner that all the elements probability of x attaining the value x, uh, sorry, probability of x attaining value xy and sum over that over all I should equal to 1 if xi belongs to E.
There's a
Sorry, for
question.
all xi belongs to E.
Shama Brother, just interrupting.
Uh,
One participant want to ask, I guess.
okay.
Shayan, go ahead.
Hello, am I audible?
Yeah, yeah,
Yes, you
sure.
are.
Can you explain what is countably infinite?
Yeah, sure. Sure. Okay. Mm, wait a minute. Yes. Yeah. So, suppose we have a bucket of balls. Okay. Okay. I can count them, and there's a finite number of time when the balls in the bucket will be empty. No balls will be left, right? So,
Yeah,
counting gonna be terminated at a particular point of time, right? And at that point of time we'll have a number with us, so in this scenario, when we have a number with us while counting, this scenario is called finite scenario, right? So the number of elements can be defined using a number. But what if that is not possible? So, no matter how much effort or time you are giving, the counting will never gonna be ended, right? So in this scenario, we call it infinite scenario. Now there are two parts of infinite scenario. One is countable and another one is uncountable. Okay, so what is countable? Suppose you are counting uh, the natural numbers. Okay, so you can count natural numbers, you can identify the distinct natural numbers, right? Suppose 1 and then comes 2, then comes 3, but can you ever get rid of counting natural numbers? Can you ever get a finite number, or not, whatever, any number that signifies the total number of natural numbers in the world or maybe in the universe? Can you get one?
No.
Okay. But in this scenario also, you can identify the natural number distinctly, right? You know what natural number comes after 2 or maybe after 2000 or maybe after 2 billion, right? But what if you are counting in such a situation where you don't know what comes after something? Okay, suppose you have taken a rational number 1 by 7. Okay, now can you tell me what is the exact next rational number exist immediately after 1 by 7?
No,
You can't,
it
right?
cannot be possibly told because
Yes,
between two
exactly.
rational number there are infinite rational numbers.
Exactly. So you can't identify them distinctly. Also, you can say that you can't identify the next part element, right? Whenever you are counting one element, you cannot determine what the next element is. But in case of countability, you can determine the next element, right? So this type of scenarios are called uncountable infinite, because this is such a scenario where counting also doesn't come into the picture. Counting is also not valid. If you don't even know what is the next element, you can't count it, right? Suppose you are counting your hairs, right? So you know what the you can identify the next hair you gonna count. But if you are counting drops from a bucket of water, you can't. You don't know where the drop is lying, right? Am I making sense?
Yeah, yeah, I got it.
uh, Clear?
Yeah,
Sin-
I got it. Thank you.
oh, okay, thank you. Suppose there are so many situations where we can get uncountable infinite. Like suppose you are measuring someone's height. Okay, and if you are not restricting yourself to any scale, suppose you are not restricting yourself any in scale or centimeter scale, and you are not approximated, then it's a uncountable infinite, right? Suppose you have someone standing in front of you having maybe 176.77 centimeter of height, and someone is 176.773 centimeter of height. You can't tell that there's no height variable or a height value in between those numbers, right? So this is an example. Okay, so I'm getting back to the old discussion, that discrete random variable. Okay, I'm assigning probability to the jump points in such a manner that all the jump points can be added, probability of all the jump points can be added, and it will give me 1. Okay, and probability of such a point which doesn't belong to E will be assigned as 0. Okay, Now, what does this probability measure is actually measuring? Look at this graph. At this point only, some arbitrary amount of weight or mass is being added to the function df, the distribution function, so that it can grow a little and take a little step ahead, right? So something, some mass or some value, some weightage is getting added at these jump points, right? That is what being measured by this function p of x equal to x, attaining the value x for all x belongs to the jump point set. Okay, this function is popularly known as probability mass function or PMF. Okay, any doubt, guys? Any doubt regarding this? If no, then I gonna uh, conclude our topics with a last topic, um, that is mixed type of random variable. Okay, so what is a mixed random variable? I have seen, if it is discontinued, then it is discrete, right? If it is continuous, then it is continuous. So what is mix? It is a binary decision, right? Either it will be continuous or not. Discontinuity point will be there. So, but there's a scenario. Suppose a df is going like this. I'm not going into very deep of the particular topic mixed random variable. I just gonna draw a distribution function so that you can get a idea. Okay, suppose what we seen in case of continuous random variable, this is an example of continuous random variable distribution function, right? In case of discrete, we saw this being elevated, right? But it's being elevated with a line parallel to the axis, right? But it could oftenly happen where these lines are not parallel. Okay, suppose this scenario. In this scenario, the lines, the graph is not parallel to the x-axis as well as discontinuous. In this scenario, we interpret such random variables as mixed type random variable. Okay, any doubt? I guess this was helpful for you guys. Uh, and that was it. That was my part. Uh, I guess random variable was not purely random for you guys. And so I'm winding up. So if you guys have any query, you can reach us through the WhatsApp group, or you can join the WhatsApp group by the filling out the membership form. And yep, that's it. Let's wrap up, guys. Any question or any feedback from your side? Okay, I guess